So for problem 10.22, we ask to do the following. So we have part A and part B. So for part A, we want just to find the first derivative, the second derivative for a given parametric function. So in other words, we want to find what is our dy over dx, and what is our like d squared, d squared y dx squared. Okay, and we given this parametric equation, x is equal to 2 sine t, and y is equal to 3 cosine t. So, and again, like we restrict our like t between 0 and pi. For the first derivative, you shouldn't experience any problem. You remember that if we're going to take the first derivative of our parametric function, then on the top, I'm going to find y partial y derivative, and I'm going to put like this t. So that means t derivative corresponding to t. Corresponding to t. And on the bottom, I'm going to put x prime of t. And then if I have that x is 2 sine t and y is 3 cosine t, then I know that x prime is going to be 2 cosine t, and y prime is going to be minus 3 sine t. So from there, I'm going to get that my derivative is going to be minus 3 sine t divided by 2 cosine t. By the way, this style that I do the problems, if you don't know how much details you need to write in your midterms, homework, etc., like this is enough. Okay, okay, so the next challenge is to finding our second derivative. So I want to find d squared y dx squared. But let's remember, like, what is the second derivative? The second derivative is when you're going to take your first derivative, yes, and we're going to take derivative of our derivative, because if you're going to take the first derivative over here, like first derivative, it's a function. So what do I mean by that? If you have a function y is equal to x squared, when you're going to take your derivative y prime, it still is going to be equal to 2x. And 2x is a function. So what you can do, you can just take one more derivative, which is going to be y double prime is equal to 2. So, but this derivative, as you remember, like from calculus, you can rewrite as d over dx of dy dx. Because like derivative of y prime is equal to f prime of x is equal to dy over dx. But I can just write this as d dx of y. So like this over here symbol means like take derivative of the function of y. And so that's what is going on here. I'm taking derivative corresponding to x of the function dy over dx. And then we're going to do the same trick. We're taking derivative of some function. So we're going to have d of dy over dx over dx. But this function, when I found derivative over here, there's going to be a function in terms of t. And here I have dx. I have that my x is also a function in terms of t. So I'm doing the same trick. So the second derivative is going to be to take your first derivative and take derivative corresponding to t, because I'm going to divide top and the bottom by dx, sorry, by dt. And take the second in the bottom part, dx, and also divide by dt. So in other words, the formula for d squared y dx squared is going to be derivative of the corresponding to t of your first derivative divided by dx dt. And this is the red box that I talked about last time. So every time I'm going to put something into the red box, that formula worth memorizing. Okay, so then let's compute the second derivative. I'm going to have so I know that dy over dx is equal to -3/2 sine over cosine is going to be tangent t. So then what do I need to do? I need to compute d over dt of dy over dx. Or in other words, I want to compute the derivative of -3/2 tangent t prime. Can anyone tell me what is going to be the derivative of -3/2 tangent t?
-3/2 secant squared t.
Yeah. So in other words, it's going to be -3/2, and secant squared t is going to be just 1 over cosine squared t. Okay. So right now what I'm going to do, should I keep the derivation or not? Yeah, I'm going to just erase this part. We don't need this part. Then what I'm going to have, so on the top, I'm going to have -3/2, 1 over cosine squared t, -3/2, 1 over cosine squared t, divided by dx, the x prime is going to be 2 cosine t. So that's going to be equal to -3/4, 1 over cosine cube t. Okay. So our second derivative is going to be, okay, can anyone tell me if I want to answer if my curve is concave up or concave down, what do I need to do? So concave up, like slash down. The examples that you need to remember, that if I have parabola, let's say y is equal to x squared and y is equal to -x squared, we know the graph of each parabola. So the first one is going to point up. I'm going to have parabolas that look like this. The second one is going to point down. So this is going to be concave up. This one is concave down. And the way to memorize, like to understand, is y double prime is equal to 2, so it's positive. So that's why we're going, when you're going to have positive second derivative is going to be concave up, and negative second derivative is going to be concave down. So to answer the question, if my original curve is concave up, I basically need to find for each value of t, so d squared y of dx squared is -3/4 times 1 over cosine cube t is going to be positive. But here, like, I'm going to give you a hint. So what we need to do, we need to remember like the definition of the cosine. Like the sign of this expression depends only on the sign of cosine cube of t. But we have minus sign here. So that's why we want to have cosine cube of t to be negative. So that's why we're interested where is my cosine is going to be negative. But we know that cosine is positive in the first and the fourth quadrant, and negative in the second and third quadrant. So using this fact, you can finish this problem. Okay. Did I answer the question about problem 2.2a?
Yes, thank you.
Yep. How was about 2.2b? 2t cube plus 3t squared minus 12t, and y of t is equal to 2t cube plus 3t squared plus 1. 3t squared plus 1. Okay, so let me send the link to the worksheet. Give me a second. So for that problem, what do you want to do? We're interested to find horizontal and vertical tangent lines. So this is going to be linked to the worksheet 10.1, and this is a link for the worksheet 10.2. Okay. So we want to find horizontal and vertical tangent lines. So let's just sketch some function that looks, it's not actually a function. Oh, no, let's sketch like this. And you can see that this is going to be your horizontal tangent line. And this line over here is going to be our vertical tangent line. Okay, can anyone tell me what is the slope for the horizontal tangent line? Then to figure out for which t we have horizontal and vertical tangent lines, then you just need to find your derivative. But remember, your first derivative is going to be just dy over dt, and your second derivative is going to be dx over dt. So here we're going to have two scenarios. To find the horizontal tangent lines, what do we need to do with this expression?
Can't we just find when dy dt is 0 and dx dt is defined?
Perfect, yes. So for horizontal tangent line, if you want to find it, we need to do set dy to dt is equal to 0 and find those t. And then do you see like when dx over dt is going to be 0, then this expression is going to be undefined. So that's why to find vertical tangent lines, we need to set dx over dt to be equal to 0. Okay, and doing that, let's just find the, sorry, what is, did you say something? Here. Then it's going to be 6t squared plus 6t minus 12. And this, and y prime is going to be 6t squared plus 6t. That's it. So you can see in both cases you have two quadratic equations. You can find their roots, and the corresponding roots are going to give you either horizontal or vertical tangent line. Okay, and here we're done with problem number 2. I can just do like, let's do this one. So 6t is equal to t plus 1. Yes. So we can see that y prime of 0, sorry, y prime of 0 is going to be exactly when t is equal to 0 and t is equal to -1. So that's why for these two values of t, I'm going to get so this is going to be a solution for worksheet 10.16. So what do we have in this case? We have a parametric equation of the form x is equal to t plus 1 over t, and y is equal to t minus 1 over t. And you can see that for this parametric equation, they didn't mention what are your parameters of t. So here you need to just assume that your t goes from -infinity to +infinity, but you can see that your t cannot be equal to 0. So that's why our restriction for t is going to be exactly from -infinity to 0, union from 0 to +infinity. Okay. So in other words, the idea is if you don't have the restriction for t, you assume the t from -infinity to +infinity, and you find for which points, like the for which points doesn't work inside your parametric function. So the first part A, I want to show that that is hyperbola. We know two equations of hyperbola. The first equation is x times y is equal to constant. And the second equation of hyperbola is either x minus y squared is equal to constant. But this is kind of the same as y squared minus x squared is equal to constant. Where the equation, the graph of the first one is going to look something like this. And the graph of the second one is going to look something like this. So basically, the difference between these two hyperbolas, they're the same hyperbola, but it depends how you rotate your coordinate axis. So for example, you can get the second hyperbola from the first one if you're going to rotate your coordinate axis by 45 degrees. So it's by pi over 4. And you can see you're going to get the same hyperbola. So to check that this is a hyperbola, we just need to either, if you're going to multiply x and y here, you can observe that it's not going to be equal to constant, but let's try to do the following. Let's try to use the second equation over here. So for the second equation, I'm going to have x squared minus y squared is equal to t plus 1 over t squared minus t minus 1 over t squared is equal to. The first is going to be t squared plus 2 times t times 1 over t plus 1 over t squared. And then it's going to be minus t squared minus 2 times t times 1 over t plus 1 over t squared. So you can see t and t will get canceled over here. So I'm going to obtain t squared plus 2 plus 1 over t squared minus t squared plus 2 minus 1 over t squared. So these two factors are going to cancel. So that is going to be equal to 4. So in other words, we're going to take our parametric equation, plug in into this Cartesian equation, and we're going to get that our parametric equation satisfies this Cartesian equation. So that is going to be kind of the our parametric equation is going to have this Cartesian form. So in other words, here we use the second approach from the first lecture when we eliminated the parameter to find the shape of our graph. So in this case, let's sketch it. So the idea to sketch, to know the hyperbola from this picture over here, I need to know what is my x intersection, yes? So you can see that to find this intersection points over here, your y component is going to be 0. So that's why if I'm going to set y is equal to 0, I will have x squared is equal to 4. So x is equal to plus minus 2. So that's why I'm going to have point here and point here. And remember, I'm going to sketch my graph dashed because I don't know how my point moves on this graph. Okay. So this is so far the solution for the first problem. Let me, I'm not done yet. It's the graph. Okay. So by this point, we're done with part A. We show that it is hyperbola. Okay. So for part B, which range of our stig is the left branch of the hyperbola? The right branch. Okay. So for that, we just need to plug in points. Yes. So we have this equation over here. And remember that you can think about our boundaries for t as like kind of this real line when there is no 0. So this is 0, this is positive infinity, this is minus infinity. So let's choose some point. Let's choose point t is equal to 1 and see what I'm going to get. When t is equal to 1, I'm going to obtain, so x is going to be equal to 1 plus 1, which is 2, and y is going to be equal 1 minus 1 is 0. I just take this component and plug it in inside those equations to find t. So for t is equal to 1, I'm going to obtain this point over here. Okay, and then right now we can analyze. So let's take this point t is equal to 1. So what we can do, we can either send t to infinity or send t to 0. Then 1 over t is going to go to 0. And the only term which are going to matter is like t. But when you send t to infinity, then x and y go into infinity. So we're going to have this direction. And since we know that when t goes to infinity, we go kind of this way, that means that we're going to have this direction for our parametric curve. And if we're going to go from 0 to, if you're going to send t to 0, you can see then this term is not doesn't matter. And the only terms that matters are over here. But when t goes to 0, then 1 over t goes to infinity. Yes. But negative 1 over t are going to go to negative infinity. So that's why y is going to have a negative value. So this is going to be the cover for my Cartesian graph using this parametric equation when t changes between 0 and positive infinity. Okay, and you can see there, like, so there is no ending point, no initial point. We have only direction. So I'm going to stop here just for a second before I'm going to move on to part C and see if you have any questions. So let me. Okay. So for part C, what do we have? We want to compare this parameterization equal to t plus 1 over t and y is equal to t minus 1 over t with this parameterization, x is equal to t squared plus 1 over t squared and y is equal to t squared minus 1 over t squared. So do you guys have any ideas what does it mean, like, if you want to compare them? So what did you observe if you're going to take the first parameterization and the second parameterization? Yeah, let me give you kind of a hint. So let's take x is equal to t, y is equal to t squared, and x is equal to t squared, and y is equal to t to the fourth. Can you just sketch in your notes this those two parametric equations when t changes between 0 and 2? So the first one over here, when t changes between 0 and 2, we're going to have when t is 0, 0, 0, when t is 1, 1, 1, when t is 2, 2, 4. Yes, as we did last time. And this is going to be my graph. But the second one, if I'm going to have 0, 0, good, 1, 1, good. When I'm going to have 2, I'm going to have 4. And then I'm going to have 4 times 4, 16. So you can see that if your first graph, let's say I'm going to use green color, look like this, then for second parameterization, this is going to be the difference. So basically, when I'm going to square my parameter for the first parameterization, the particle on the graph is going to move faster. Because you can think about this t as time, and you can see for the same amount of time, the like, let's say the red particle covered more distance. So we have let's say like comments or like remark. So notation in 10.12, so number 10.12. We have the following. I said it's C is x, y that belongs to R2 of x squared plus y squared is equal to. So this notation is called like a set notation. Notation. So the first part before like this mark, this like type of elements that belong to C. Belong to C. And the second, like this part, like how it's called a rule, like or like a special property, property that they must satisfy. So it's like in simple words to explain. So let me show you what is C in this case. So you can see that the type of elements that we have something elements that belongs to R2, and this R2 is a plane. It's just a short notion for the plane, Cartesian plane. So that's why we have in our set an elements of Cartesian plane xy. But they have a special property. Like all these points must satisfy x squared plus y squared is equal to 1. Can anyone tell me what is the graph of x squared plus y squared is equal to 1? Like 1, 0. You ask, does this point satisfy this equation? Like yes. So does this point going to belong to C? If you, for example, going to choose a point negative, like 1, negative 1, then this point doesn't satisfy that property. So that means that point doesn't belong to C. And we're going to indicate all points that belong to C by this red line. So this is going to be your C. So it's, in other words, it's just a way how to describe certain points in a plane. So similar description we're going to use for different shapes in 3 dimensions. Let's take a circle. X squared plus y squared is equal to 4. And I want you to describe the movement of the particle that starts at the point 0, negative 1, and going to move clockwise to the point, 0, negative 2, and is going to move to the point negative 2 and 0. So this is your initial point A, this is your ending point B, and that is your direction. So take a couple of minutes to think about this problem, and then we're going to discuss it together. Let's try, for example, x to cosine theta, yes, and y is equal to sine theta. And on the right, I'm going to have a picture, and let's say t changes between negative infinity and positive infinity. So can anyone tell me what I'm going to have on the right-hand side? What is going to be the orientation of my circle in that case? Clockwise or counterclockwise? Yes, because when t is equal to 0, I'm going to have this point. And when t is equal to pi over 2, I'm going to have this point. So if I want to change my orientation, what do I need to do with this expression over here? So right now I'm going to switch my cosine sine, and then I'm going to have the opposite orientation for my circle. And again, because when t is equal to 0, I'm going to have this point, which is 0, 2. And when t is equal to pi over 2, I'm going to have this point. Okay, perfect. So right now, at least we know what parameterization do we need to use, yes? For so to finish the problem, what do we need to specify?
The range of t.
Yeah, and so what is the range of t in this case? Perfect, yeah. From pi to, because if this is t is pi over 2, then next t, you can check this is going to be pi, and this is going to be 3 pi over 2. So basically the idea, if I'm going to ask you to describe the movement of the particle following some path, so first you need to find parameterization that is going to be that is going to have the same orientation, like direction, with the paths that I ask you to do, and then you just need to restrict your t, and that's it. Okay. So we did this one. Let's do also as a practice this one. Again, this problem next problem is going to be slightly. We did this problem. Okay, well, let's see. So we have like a couple of minutes to do it. So let's say we have a parabola. Y is equal to x squared. So the paths that I want you to describe, you start at negative infinity, you go towards the origin, and then you come back using the same path. So can anyone tell me the description of that parabola? So this is from t negative infinity to 0 and to positive infinity. So what is going to be x and y in this case? And you know what, like, let's do like 2 different parameterizations just to see a difference. Okay, that's a good, let's try that. So we have x is equal to t and y is equal to t squared, yes? So then what is going to be your bounds for t? Infinity to infinity, yeah. So we can see that if t is going to change from negative infinity to 0, yes? So in other words, yes, I am indeed going to get this part of parabola. But when t is going to change between 0 and positive infinity, what is going to happen with your x? And for the both cases, we need to have that our bounds for t are between negative infinity and positive infinity. And perfect. So in this case, yeah, we're going to get this graph over here. Okay, so we're going to do like a short break before the actual lecture time for when I'm going to talk about introduction to polar coordinates. So for section 10.1, 10.2, like the main goal was to understand parametric equations.